Hi class, in this lecture we continue our study in chapter 15 by moving into section 15.7, talking about triple integrals in cylindrical coordinates. Now this kind of type of triple integral is really just an extension of polar coordinates that we learned in for double integrals, just with the z component to the coordinate now. That's what makes it triple. Okay, so let's talk about how you evaluate triple integrals with cylindrical coordinates. Okay, so suppose you have this region E right here. Okay, and when you look at the projection of E down into the XY plane, you can see that it's going to be conveniently described with polar coordinates. So the inner value here, the inner radius here is some function of theta, the outer radius is some function of theta, and this region goes from theta is equal to alpha to theta is equal to beta. Okay, so in particular, suppose that this function f that's going to describe this E is continuous and x and y exist in the xy plane, and this u1 down here and u2, the top part of it, are both functions of x and y. This is where, as I said, that d in the xy plane is given in polar coordinates. We know the following here. Okay, our triple integral over this region E here is going to be equal to the double integral over d. Okay, that's the polar coordinate part. And then inside the single integral from u1 to u2. All right, but actually what we can do here is we can convert this right here to polar somehow. Okay, so but to evaluate double integrals in polar coordinates, we're going to have the following here. So I'm going to change these two integrals over the region D to polar. And then you'll notice in here, my u1 and u2 are no longer functions of x and y, but of r cosine of theta and r sine of theta. Okay, and then we're going to integrate this with respect to r dz dr d theta. And this is going to be the formula for triple integration in cylindrical coordinates. Okay, so what it says here is we convert a triple integral from rectangular to cylindrical coordinates by writing, again, x is equal to r cosine of theta, y is equal to r sine of theta, and we leave z as it is. So notice that the z doesn't change, okay? And this is using the appropriate limits of integration for z, r, and theta, and replacing that dv by r, dz, dr, d theta, as I said. Okay. So it's worthwhile to use this formula when E is a solid region easily described by cylindrical coordinates, and especially, this is important, especially when the function f of x, y, and z involves the expression x squared plus y squared. Okay, then it's, that's a quick giveaway that you should try to evaluate this triple integral with cylindrical coordinates when you see this. All right, so I want to do one practical application of this, and it just talks about setting up the integral. And then you'll see that once you set the integral up, like a lot of the previous problems, it actually becomes pretty trivial. The hardest part is setting up the integral. Okay, so we have this solid E in figure 8 that you see here, lies within the cylinder defined by x squared plus y squared equals 1. So this cylinder here, the outer part of the cylinder is defined by this. Below the plane, z is equal to 4, so it stops up here. And above this paraboloid, z is equal to 1 minus x squared minus y squared. And you can see that paraboloid right here, okay? So what's going on here, what we want to talk about is the density of this. So the density at any point is proportional to the distance from the axis of the cylinder. Okay, so what I want to do, not find density, I want to find the mass of E. I want to find the mass of this object. All right, so in cylindrical coordinates, let's talk about how we set this up. The radius is equal to 1. You can see that right here. Okay, x squared plus y squared is equal to 1, so that's telling me the radius is 1. And the paraboloid is z is equal to 1 minus r squared. So we can write this as the following. Okay, the area, this E is defined. Okay, the radius is going to go from 0 to 1, as I said. Theta, okay, is going to go from 0 to 2 pi because we're going a full rotation around the circle here. And my z here, it's going to be bounded below by this 1 minus r squared, okay? And the top is 4 up here. Okay, so since density is proportional to the distance from the z-axis, the density function of this is equal to k times the square root of x squared plus y squared. Okay, and then here's the thing. We know that x squared plus y squared is equal to r squared. So the square root of that has to just be r. Okay, this k here is what we call, or is what's referred to as the proportionality constant. All right, so once we have that set up, look. Here's our formula. We got a function now in here. So now we have r, dz, dr, d theta, and we've got our bounds of integration defined. So this integral, okay, therefore the mass of this is the triple integral over the region, okay, our integrating the density function, is just the following. We're going to integrate, as I said, from 0 to 2 pi. Okay, the radius went from 0 to 1. And what did z go from? It went from 1 minus r squared to 4. And then this right here is my function times r. So just integrating this, okay, piece of cake, all right? This is going to integrate as the following here, and I'm just going to plug in. This simplifies this to when I do 4 minus plugging in 4 using the fundamental theorem of calculus minus plugging in 1 minus r squared, we get the following. And then you can just integrate this with respect to dr. You'll get the following. And then when you integrate with respect to theta, you'll get the following down here. So it's pretty much once you get this set up, you just go through it, and it's pretty straightforward. All right, class, I hope this helped at least in terms of how you set it up, and be sure to watch the rest of the lectures in the classroom.